Displacement can be defined as the change in position of an object during its motion from start to finish. As can be seen from the displacement function of s of t, when s of t equals 0, the particle is at 0 and is at rest. Here is defined by the displacement function s of t. Whilst s of t is greater than 0, the particle is in a positive direction to the right of 0. As can be seen here with the displacement function s of t, whilst s of t is less than 0, p is negative or to the left of 0. Presented here we have a distance graph which helps define and show the particle's movement as it moves away from the origin in relation to time. Velocity can be defined as the rate of change of displacement, or it can be defined as the rate at which the position changes. As can be seen, when velocity is equal to 0, the particle p is instantaneously at rest. As can be seen, when v of t is greater than 0, the particle is moving to the right. As can be seen, when v of t is less than 0, the particle is moving to the left.
Here we have a graph displaying the velocity of a particle in relation to time. This shows the rate at which the position changes and whether it's moving away from the origin or towards the origin. Acceleration is the rate of change of velocity and can also be described as the increase in speed or rate. As you can see here, when acceleration equals 0, the particle is either at a maximum or a minimum. For example, a car is about to start accelerating, or the car is about to put their brakes on to decrease their acceleration. Here we can see when the acceleration is greater than 0, the particle is gaining speed throughout its movement. On the other hand, when the acceleration is less than 0, the particle's speed is decreasing as it tends towards 0. With a graph of acceleration, it's quite easy to determine what's happening to the particle. If it's greater than 0, it's increasing speed. If it's resting on 0, there is a minimum or a maximum. And if it's less than 0, the speed is decreasing. And the values on the side determine how fast the particle is moving.
If velocity and acceleration are the same, then the speed of p will be increasing. But if velocity and acceleration are different, that is, if one is negative and one is positive, then the speed of p will be decreasing. But how is this related to applications of calculus? The derivative of some function is also known as dy over dx, which is the rate of change of y with respect to x.
When you want to find the rate of change of displacement, you simply derive the displacement function. This then gives you the velocity of that function. Therefore, velocity is the derivative of displacement. Same as the displacement function, if you are wanting to find the rate of change of velocity, you simply derive the velocity function, which then gives you acceleration. Thus, acceleration is the derivative of velocity. Because acceleration is the derivative of velocity, and velocity is the derivative of displacement, that means that acceleration is the second derivative of displacement. Here we have all three graphs side by side to understand what the derivative or rate of change has on the original function. In our first graph, the distance graph, we can see that the particle moves away from the origin for the first 12 seconds before reaching its maximum distance from the origin, before turning about and coming back towards. In the velocity, we can see how for the first 3 seconds, the velocity of the particle accelerates in the positive direction before maintaining a constant velocity between 2.5 to 12.5 seconds, where the distance is at its maximum, before becoming negative in that it's returning back towards the origin point, and then finally leveling out between 17.5 to 20 seconds. In our third graph, we can see that the acceleration of the particle happens for the first 4 seconds of its movement, whereby its acceleration is 0 for the next 3, followed by a negative acceleration between 7.5 to 17.5 seconds, before this acceleration then becomes positive again. All three graphs coincide with different key elements of the function.
Average velocity is equal to change in position divided by the change in time. This is given by the formula s of t2 minus s of t1 divided by t2 minus t1. Here we will demonstrate an example of average velocity of some function. If we have the function s of t equals 6t minus t squared of interval 0 to 3, we calculate the velocity by substituting 3 equals t2 and 0 equals t1 into the formula previously given. After substitution, you get 9 on 3, which simplifies to 3, giving an average velocity of 3 meters a second. Instantaneous velocity is the velocity of an object at a single point in time, and is given by the derivative of displacement. Here we show an example of instantaneous velocity, given the function s of t equals 6t minus t squared. To find instantaneous velocity at a certain time, you must derive the displacement function, which gives v of t equals 6 minus 2t. To find the instantaneous velocity at a certain point in time, substitute a value of t into the velocity function that was just calculated. For example, to find the instantaneous velocity at 2 seconds, we substitute t equals 2 into our function, which gives us an instantaneous velocity of 2 meters a second.
Average acceleration is equal to the change in velocity divided by the change in time. This is given by the formula v of t2 minus v of t1 divided by t2 minus t1. Here we show an example of average acceleration given by the function v of t equals 6 minus 2t of interval 0 to 3. If we sub t2, which equals 3, and t1 equals 0 into the formula given before and simplify, we are left with average acceleration of minus 2 meters per second per second. Instantaneous acceleration is the acceleration of an object at a single point in time and is given by the derivative of velocity. Here we show an example of instantaneous acceleration given by the function v of t equals 6 minus 2t. To find instantaneous velocity at a certain time, you must derive the velocity function. This gives an instantaneous acceleration of minus 2 meters per second